Our pale blue dot, Earth, doesn't just spin on its axis and orbit the sun. It is part of a much larger cosmic dance, a journey that takes us through the vast expanse of the Milky Way galaxy. We are on a much grander journey, a cosmic waltz through the Milky Way galaxy. This journey is not just a simple orbit around our star, it is a voyage through the galaxy's spiral arms, filled with stars, dust, and cosmic wonders. This journey isn't just a sightseeing tour, it can have real impacts on our planet, including its climate. The regions of space we travel through can influence Earth's weather patterns and even its geological history. Imagine our solar system as a ship, sailing through the vast cosmic ocean of the Milky Way. Just as a ship navigates through different waters, our solar system moves through various regions of space, each with its own unique properties. Just as a ship encounters storms and calm waters, our solar system encounters regions of space with varying properties. These regions can be dense with interstellar dust or filled with energetic particles, each affecting our planet in different ways. These encounters can leave their mark on Earth, shaping its climate over eons. The cosmic environment we pass through can influence everything from atmospheric conditions to the development of life itself. One such encounter took place around 14 million years ago, a time when our planet experienced a significant climate shift. This shift was not just a minor change, it had profound effects on the Earth's ecosystems and the evolution of species. During this period, our solar system passed through a region teeming with young stars and interstellar dust. This cosmic neighborhood was bustling with activity, and its influence on Earth was substantial. The interstellar dust and energetic particles from this region interacted with our planet's atmosphere, leading to changes that scientists are still trying to fully understand. These cosmic encounters are like chapters in Earth's history, each leaving its own unique imprint. This encounter, like a gust of wind on our cosmic ship, left behind traces that scientists are only now beginning to understand. By studying these traces, we can learn more about the forces that have shaped our planet and continue to influence it today. Our solar system resides within a spiral arm of the Milky Way galaxy, a vast and intricate structure that stretches across the cosmos. This particular spiral arm is known as the Orion Arm, a relatively small but significant part of our galaxy. The Orion Arm is home to vast clouds of gas and dust, the essential raw materials from which stars are born. These clouds, often called nebulae, are the stellar nurseries of the universe. As we journey through the Orion Arm, we inevitably encounter these star-forming regions where the birth of new stars is a constant and dynamic process. Such regions are dynamic and chaotic, often teeming with young, hot stars that emit intense radiation. These stars are in the early stages of their life cycles, burning brightly and shaping their surroundings. This radiation can ionize the surrounding gas, creating what are known as HII regions, which are bubbles of hot, glowing plasma. These regions are often visible as bright patches in the night sky. These star-forming regions are also rich in interstellar dust, tiny particles of matter composed of elements like carbon, silicon, and iron. This dust plays a crucial role in the formation of planets and other celestial bodies. This dust is a byproduct of stellar evolution, formed in the hearts of dying stars and scattered throughout the galaxy. As stars reach the end of their life cycles, they expel their outer layers, enriching the interstellar medium with these elements. As our solar system traverses the Orion Arm, it can sweep up this interstellar dust, potentially impacting Earth's climate. The interaction between interstellar dust and our planet's atmosphere is a subject of ongoing scientific research, revealing the interconnectedness of cosmic and terrestrial phenomena. Interstellar dust isn't just a passive passenger on our cosmic journey. It carries with it the fingerprints of its origins, including traces of radioactive elements. These elements, forged in the nuclear furnaces of stars, can have significant effects on planetary atmospheres. One such element is iron-60, a radioactive isotope of iron produced in supernova explosions. When interstellar dust carrying iron-60 enters Earth's atmosphere, it can deposit this radioactive material onto the planet's surface. Iron-60 decays with a half-life of 2.6 million years, releasing energy in the form of gamma rays. While the amount of iron-60 deposited by interstellar dust may be small, its radioactive decay could potentially impact Earth's climate over long periods. Around 14 million years ago, Earth's climate underwent a significant and transformative shift known as the Middle Miocene Climate Transition. This period is a crucial chapter in our planet's history, marking a dramatic change in the global climate system. This period marked a transition from a warmer, wetter climate to a cooler, drier one. Lush, verdant landscapes that once thrived began to give way to more arid and cooler environments, altering the very fabric of ecosystems across the globe. The exact causes of this transition are still debated, but scientists believe it was likely driven by a combination of factors. These include changes in Earth's orbit, which affected the amount of solar energy reaching the planet, volcanic activity that released particles and gases into the atmosphere, and potentially, the influx of interstellar dust that may have influenced atmospheric conditions. During the Middle Miocene Climate Transition, global temperatures cooled significantly. This cooling led to the expansion of ice sheets, particularly in the polar regions, and a consequential drop in sea levels. These changes reshaped coastlines and altered ocean currents, further impacting the global climate. These climatic shifts had profound impacts on life on Earth. Many species faced extinction as their habitats changed, while others adapted to the new conditions. This period saw significant evolutionary changes as life forms evolved to survive in the cooler, drier climate. While the precise role of interstellar dust in this transition remains an area of active research, scientists are intrigued by the possibility that it may have played a role in tipping Earth's climate towards a cooler state. Understanding these ancient climate shifts helps us comprehend the complex interplay of factors that drive climate change, offering insights that are relevant to our current and future climate challenges. Section 5. Radioactive fallout, a possible climate catalyst. The deposition of radioactive elements like iron-60 from interstellar dust could have influenced Earth's climate in several ways. The energy released during the decay of these elements could potentially ionize atmospheric molecules, leading to the formation of clouds. Increased cloud cover could have reflected more sunlight back into space, contributing to global cooling. Furthermore, the presence of radioactive isotopes in the atmosphere could have affected the chemistry of the atmosphere, altering the balance of greenhouse gases. While the exact mechanisms by which interstellar dust may have influenced Earth's climate during the Middle Miocene are still being investigated, it's a fascinating example of how seemingly distant cosmic events can have tangible impacts on our planet. Section 6. Ancient Shifts, Modern Parallels. A tale of two time scales. While the Middle Miocene climate transition was a significant event in Earth's history, it's important to note that it occurred over hundreds of thousands of years. The changes in climate during this period were gradual, allowing life on Earth time to adapt. In contrast, the current warming trend our planet is experiencing is happening at an unprecedented rate, primarily due to human activities that release greenhouse gases into the atmosphere. The rapid pace of modern climate change poses significant challenges for ecosystems and human societies. Unlike the gradual shifts of the past, the current warming trend is happening too quickly for many species to adapt, increasing the risk of extinctions and disrupting delicate ecological balances. Section 7. The Anthropocene Epoch, Humanity's Imprint on Climate. Scientists have coined the term Anthropocene to describe the current geological epoch, one in which human activity has become the dominant influence on Earth's climate and environment. Our reliance on fossil fuels, deforestation, and other activities have led to a dramatic increase in atmospheric greenhouse gas concentrations, trapping heat and driving global warming. The consequences of this rapid warming are already being felt worldwide, from rising sea levels and more extreme weather events to shifts in plant and animal life cycles. The longer we continue on this trajectory, the more severe and irreversible these impacts will become. Section 8. A Call to Action, Protecting Our Pale Blue Dot. Understanding Earth's climate history, including the potential influence of cosmic events like our passage through star-forming regions, provides valuable context for our current situation. While our planet has experienced climate shifts in the past, the current warming trend is driven by human actions, and its consequences are unfolding at an unprecedented rate. This realization should serve as a call to action. We have the knowledge and the ability to transition to a more sustainable future, one that prioritizes renewable energy, responsible land management, and international cooperation. By understanding our planet's history and the consequences of our actions, we can make informed choices to protect our pale blue dot for generations to come.